So thank you for coming along, everybody. I know it's hard for us to get out of our houses on a Friday when we like to work from home these days, so thanks for making the effort. We're going to do a real fast, high-level talk about SQLite and SQL. So a little bit about me. I'm Steve. I'm an engineering manager at ANZ on the mobile banking team. And you can contact me on my work address, or you can find me on Cocohead Slack is probably the best way to contact me. Things you don't know about me is, as I say, I started work doing mobile engineering last century on these kind of devices. I originally was in the construction industry. My old man had a building company, and I saw the opportunity to write some applications for that industry, like doing defect inspections and site notices and things like that, and used the Palm Pilot to explore that. Which was pretty cool, pretty difficult. I've used everything, Symbian, Windows PC, you name it. I was very relieved when Apple came out with iPhone OS, and I learned Objective-C, and I've been doing that kind of stuff ever since. I love cooking. I've got a big smoker. My wife's always aghast that I bring huge bits of meat into the house to break up and smoke and make brisket and everything. And a bit like Baz next door, I'm a hockey tragic, so I've been to many Olympics and World Cups and kind of travel the world with a group of guys, and we have great fun. We know all the players. Australia, Kookaburras won the World Cup in 2014, and I was there drinking beer at the World Cup trophy, which was pretty cool. So this talk is absolutely not a tutorial, right? We're going to move really quickly, and all I want you to do is to think about your storage layer, your database. Are you just using it for storage, or is there more that you could think about doing with that layer of your application? So quick agenda, we're going to look first, we're going to have a little bit of fun for 10 minutes looking at the history, the computer science behind relational databases. So that everyone's on the same page, we'll look at some very basic essentials for using SQL on mobile, in fact, in general. We'll look at some cool things that SQLite can do, some of which you'll know, maybe some things you've not considered yet. And lastly, we'll look at a great package, GRDB, which allows us to, which is a wrapper for SQLite on Swift applications, and that introduces some really great functionality that allows you to do some cool stuff on your applications. So the history of relational databases is pretty cool. Like, there's no AI here, right? But now we're in the kind of AI arms race, and we've had the .com kind of arms race previously. If we go back into the 1970s, it was kind of relational databases that everyone was working on. And we can meet this guy, Ted Codd. He's an Englishman. He won a scholarship to study chemistry and mathematics at Oxford Uni. He was a pilot. He flew Sunderland flying boats in the Second World War. And then afterwards ended up in San Jose working for IBM. In those days, IBM were like a huge computer science research place. Back in the day, we had in the late 60s and early 70s, we had databases. They were called like hierarchical databases, and to get a report, you basically had to write a custom application, specific to the schema of the database. And Ted Codd kind of thought about this, and he released this really seminal paper called A Relational Model of Data for Large Shared Data Banks. And his whole proposal was that we shouldn't need custom applications. We should be able to have a kind of common way of querying the data in these databases. And he introduced this concept of relations and domains, so that's the relational database. And today we would call a relation a table, and we'd call a domain a column. At the time, his paper was kind of met with a little bit of skepticism. But later, in 1981, he actually was awarded a Turing Award for this kind of fundamental word, and they actually called it one of the greatest technical achievements of the 20th century. So pretty meaningful and inspirational paper, which is pretty cool. But Codd's queries look like this. So that's not very approachable to me, right? I think it's very elegant maths. It's over my head, but that's what I'm told. But of course, it's not very accessible. If we had to write queries like this, we'd be struggling. So we can meet these new guys, Don Chamberlain and Ray Boyce, also IBM workers in the early 70s, and they looked at that previous work, those algebraic queries, and said, well, that's not something that we can really work with. They really worked on trying to turn that into something that we're more familiar with today, and that would be actually approachable for everybody, right? So their first goal was this thing called Square. So everyone, this is all acronym city here, but it didn't fly. It was still very mathematical and very confusing and unapproachable for a regular user. So they had another try, and they said, look, let's do this thing, structured English query language, and made this acronym SQL, which we probably would have been using today, except they got embroiled in a trademark dispute, so had to drop a couple of letters, and this is why we now have SQL. Which, was pretty much in the early 1970s there, very similar to what we'll see today, that kind of declarative English query language. Later on, it became standardized, so ISO and ANSI used it as a standard, and later on in the 70s, it was picked up by a company called Ingress, who became Postgres, and by this company Relational Software, who became Oracle. So those two kind of heavyweights really ensured that SQL became the standard way that we query our relational databases today. But there was still a missing thing, and we now meet Tricia Salinger, who is an IBM and ACM fellow, and she did amazing work on what's called cost-based query optimization. In fact, her work is still the basis of how all relational databases work today. And basically what that does is you declare your query. So you tell the database engine what you want. You don't tell it how to do it. This query optimization algorithm works it out itself. And basically, it tries a whole bunch of possible ways of fulfilling your request and giving you the data, and then works out the lowest cost way of doing that, so the fastest way of doing it, I guess. Later on, I'm going to tell you that in my opinion, this 50-year-old algorithm, if you employ it properly in your apps, is going to be faster than writing even modern Swift with, filters and MapReduce and all that kind of stuff. This is much more performant. Later, we can meet this guy, Richard Hipp, a bit of a controversial character. He was a Navy contractor working on damage control systems for ships. So when a ship's in kind of taking battle damage, and maybe all its systems are getting severed, so it's steam pipes, water pipes, electrical conduits, whatever, they use a database to figure out how to reroute all their systems and kind of stay active. The problem was, though, that's a kind of high stress environment. He's got this funny quote about what that's like, and he realized, well, what happens if one of the kind of connections that get severed is literally like your Ethernet cable to the database server? That's going to be pretty bad. So he kind of thought about it, and he looked at the traditional model of kind of big metal database servers at the time, and he realized that why could we not just get rid of the server completely and actually move the database into the client? So he took a sabbatical for 6 months in 2000 and wrote SQLite, which is pretty cool. So it was cross-platform, it was very small, very fast, mostly standards compliant. Even today, there's a few rough edges. Fully public domain, and now, because of that, probably the most widely deployed database in the world. So pretty cool history. The computer science behind relational databases is pretty amazing, and some really big figures. It's a shame we don't know, the history of some of these people a little bit more. But moving on, when we use relational databases in our apps, there's some basics that we need to know, and we'll just kind of get everyone up on the same page. So we make our tables. We write this schema, and that's kind of easy enough. This one has an integer primary key, which uses SQLite's internal row ID, so it's quite efficient. It's not great for distributed scenarios or for privacy though, so for non-simple tables, you'd probably prefer to use a UUID for your primary key. Primary keys are really important though. They're a type of index, which we'll talk about in a second. Interestingly, you can see here, there's a few column types. SQLite supports 5, nulls, integers, reals, text, and blob. It's actually not type safe though. So out the box, that integer column for the balance, if you wrote a string there, that would be quite fine. It would store the string without complaining at all, which is obviously a little bit of a problem for some of our type-safe modern mindset. If you don't like that, you can put the word strict at the end of the schema, and that introduces type-safe columns into SQLite. It's not very common to see that strict word in examples, but probably something I would recommend you consider. Indexes are really important in relational databases. In SQLite, they are balanced trees, which means we can find values using binary search. So rather than doing a full table scan to find a value you're looking for, it can be much more performant by doing a binary search and finding the values. You can have very simple indexes on any column, and pretty much any column that you're considering using to join tables together or using as where criteria you should consider adding an index. You can also have indexes that are multi-columns. So for example, if you knew you were always going to do a where criteria with 2 values, you could set your index on those 2 values, and then you will get your results with 1 binary search rather than 2 or 3. You can also kind of filter the values that get indexed if space is a concern. Joins, obviously, super important in relational databases. This is how we tie and relate one table to another. For example, in my world, accounts and transactions are 2 tables that are joined. SQLite supports 3 different types of joins, left, inner, and cross. In real life, it's rare to use anything but left, in my experience. So the kind of typical join that you see documented everywhere. And the last kind of introduction concept that's important is transactions. So just by wrapping your statements in a begin transaction and a commit, you ensure that everything in the middle there is executed by the database atomically. So everything will either succeed or fail and be available to roll back. That allows you to ensure your data is not corrupted, and it is super good for performance. If you're inserting a lot of data and you do it as one transaction, you'll get a lot of performance benefits by wrapping everything up in a transaction. But beyond the simple things that probably most of you already know, there's a few other things that we can look at with the database. The first thing is this cool tool, the Query Analyzer, which helps us understand if our query is written efficiently and if we have indexes that are going to make our queries performant. You can see here in line, I've run a query, and in line 6, it's saying, hey, I'm going to return the results of that query by scanning the entire table. Now, if you've got a table that's, hundreds of thousands of records, that's going to take a long time. And you can see then below that, I've added an index and asked for it to analyze that again, and it's saying, yep, we're using an index as our cost plan to return those results that you're asking for, which is great. So you go, well, how do I get access to the Query Analyzer? And the good news is if you have a Mac, well, you've already got it installed. You've already got SQLite installed. You just open up Terminal, at the prompt type SQLite 3, and you are in the environment. So you can prefix your queries with the explain query plan prefix, and that will then give you all this kind of data about how the query planner is deciding to execute your query, and you can see if you have missing indexes on some of your important columns. I would say if you've got important queries in your app, make sure you are extracting the SQL statement and running it through the Query Analyzer to make sure you're not missing any indexes. Another thing you can do is full text search, which is really, really good. We can do, we kind of can do searching using like the like keyword. So we can say, oh, give me everything where this column is like whatever with a wildcard. That's kind of slow. If you implement full text search, you get this new keyword called match, and it's orders of magnitude more performant than using like, and probably 100 times faster than using multiple like criteria, because it can search the index for all the terms all at once. And it also allows you to do things like ranking and searching for stems of words, and even using different tokenizers to find phonetic matches and things like that, which is pretty cool. It's very, very easy to set up. You create a virtual table, you use a trigger usually to keep that up to date, and then you've got access to all these kind of match queries you can see there using different patterns and things like that. So if you've got a application where you want to do local search, it's well worth considering setting up full text search. Window functions are very cool. They allow you to do a query that basically rolls up values over a period. So something like in my world, I might have to figure out what the account balances is for every time a transaction comes through over time. And window functions allow you to do that. And it's efficient both in terms of performance and memory use, or even over millions of records. As an alternative, if you loaded all those transactions into a Swift collection and tried to do some kind of map reduce, this is just going to be miles faster. Really, really powerful kind of capability. And again, it's quite easy to use. You can see right in the middle of this query, we're using this unbonded preceding rows kind of syntax, which is allowing us to input the kind of running sum into the query as it goes through. And there's a whole bunch of different sets and what they call frames that you can use to control the context of the preceding records as you're rolling through. Another really interesting thing is recursive queries, operating with common table expressions. So a CTE is kind of like a view, but is specific to the query that it's executing on. And a recursive CTE allows you to walk a graph, which is really nice. And again, much more performant than doing this with recursive Swift functions. Say you needed to, traverse a whole hierarchy, including nested leafs and all that kind of stuff. A recursive query can do that work inside the database for you. So say I had like hierarchical data like categories of a banking transaction. So I've got a parent category and subcategory and levels below that, and I wanted to get a summary of the total spend by my top level of categories. One way I could do that, with some kind of map reduce in Swift or a recursive function call, but I can do that directly with a query and get answers straight out of the query plan, which is amazing. That code you can see there will basically handle any kind of classic hierarchical data structure up to unlimited nesting levels, and it's going to work really, really quickly. Another thing is generated columns, very, very easy, but often overlooked and really, really cool. You can set up a virtual column, which is computed as it's read, kind of like a Swift lazy property, or you can have a stored column, which is computed and written and cached. And basically, I kind of view these as analogous to like a computed property on your models, except it's coming from the database query. So if we had a Swift class kind of like this, and we've added in, some contrived computed properties, that's something we have to, reason about, maintain, probably unit test. This might be easier, right? If we just had our model that looked a little bit like this. And we can achieve that by creating some generated columns in our query, which can be run through the query analyzer, and that kind of lives in our data layer and powers those kind of properties in our models. So how do we use all these tools? The best wrapper I have found at the moment is GRDB. It's been out for quite some time. Why do I like it? Well, it's open source. It's MIT licensed. It's actively developed and supported. It's a little opinionated, but that's fine. We can live with that. It works on all iOS and Mac platforms. Swift Package Manager, and it has really excellent documentation. There's a few other ones. SQLite.swift is a kind of lighter weight wrapper, and many of you might have used FMDB back in the Objective-C days. It did a similar job. So GRDB, it's really good for many use cases. At its very highest level, it allows you to do the kind of ORM kind of object type level, kind of like core data or Swift data, where you can basically extract collections of your Swift models. But it equally allows you to go into low-level SQL statements if you prefer to work that way. It does things like provide you like a cursor of results, so very memory efficient and very performant if you're dealing with large volumes of data, which we'll talk about a little more. And it also supports, which is pretty cool, custom SQL functions. So if you want to do something crazy, and your option was to compile SQLite yourself in C, which is not easy. Another option is to use GRDB custom functions, which achieve the same thing. You can get your own special SQL keywords, which you can use in queries, and you've written that in Swift, which is pretty cool. So some of the basics. It's very easy to set up. Import GRDB. Here we're using a pool, so we're going to get concurrent write-ahead log access to the database. Because SQLite itself is not multi-threaded, it's only single-threaded, so using a pool allows you to have concurrent access over threads. And I've set up like a contrived initial migration just to get an account table in there. So yeah, very little code needed to get going. If we wanted to use the kind of ORM level, so more analogous to Swift Data, for example, it offers a couple of protocols, for example, fetchable record and persistable record. And if you conform to those, GRDB will manage all the mapping and codable work for us and just spit out, as I said, arrays of these objects, which is pretty cool. And if you're going that way, it makes it very easy to update the database using a high-level Swift syntax, and equally reading from the database using those kind of protocol conformance is nice and simple. So for me, I prefer using this than like your Swift data or your core data because it can do a similar job. But if something goes wrong, I've still got access to the raw database to go in there and do things. There's a bit more magic that the GRDB does, though, which is really cool. And we start off when we have a problem, like if we write some code like this, it's a little bit dated now. And the problem is we've got to do manual refreshing of the data, right? So our what we see on screen can go stale. We've got to coordinate updates amongst different views. Maybe that introduces some performance issues on large data sets. And, it's just a lot of work to maintain and reason about that code. I could have lots of problems there. What if we could do it a different way using GRDB's value observation, which is a great feature that kind of solves that. We'll dig into that a little bit more. But basically, this gives us a fully reactive connection to our database. So some of those problems that we considered before kind of get solved. It's kind of like gives us automatic reactive updates to our data layer. How do we do that? Well, here, contrived small example to fit on a slide. We're setting up a value observer. And basically, this publisher is going to emit a new value, which is probably going to be an array of objects, every time the results of the underlying query changes. So if you imagine I had a select query on a table looking for like a whole bunch of, say, banking transactions in a banking app, anytime one of those transactions change, this is going to emit a new value and allow us to update the screen. And you're saying, oh yeah, that's great, but why, Steve, are you showing me combined today? Well, we can do it in Swift concurrency as well, which is pretty cool. Works the same way, just pure async Swift code, and that will allow us, for example, to update a published array of objects every time our database layer changes. So we're fully reactive. We set this up and we don't have to do anything. Works particularly well with Swift UI when we're writing the values out to a published property. Little bit behind the scenes on our app at the ANZ. So we hold a socket to our backend open all the time. And the backend will push new objects to us whenever there's a change. So if there's a direct debit or something on your account and a new transaction comes through, that gets pushed to us and we ingest that into our local SQLite database. And we have a value observer, a shared value observer set up that's monitoring the transactions there. When it picks up that the transaction query is changed, it emits a value, which our view models then set into our published properties, and our screens will just update with all those new values, which is pretty cool. So everything's up to date all at the same time. So like our list of transactions, the daily header, the overall balance of your account, all that kind of thing can be hung off the published property from your view model and update your view, and it's powered by this whole reactive pipeline coming from the data layer. So it's a kind of, paradigm switch from, maybe starting off doing things like this, but then, setting up this reactive pipeline to plumb everything together, which is really good. So key takeaways, if you think of anything and you're thinking about your data layer, is do use the query optimizer to make sure that you have everything indexed properly, and let Patricia's 50-year-old algorithm do the work for you. It is really fast. Think reactive. Value observers can make your whole data storage layer right through to your views fully reactive. And you can push some of the complexity down. So if you find yourself loading an array of objects in Swift and you're doing, filtering, mapping, map reduce, all that kind of stuff, have a think about it, because probably the database can do that for you and probably do it more quickly and give you less code to maintain. And also, if you put a SQLite database in your app, it gives you the ability to be offline first. So our banking app will still work. You won't be able to pay anyone, of course, but if you're offline on airplane mode, everything still works. You can look at all your transactions, you can search and do all that kind of stuff, which is very cool. So I said we'd go fast. We've gone fast, just on 20 minutes. Thank you very much, and happy to take any questions.
Thank you very much. All right, let's have some questions.
So when you are using SQLite on an app and you want to debug either the data in the simulator or a device,
yeah,
using a terminal, is there a way to do that?
Yeah. So let's say we're working on a simulator, so you can go into the app package and directly access the database, and you can open it up in whatever tool you want to investigate that, or run it on the terminal. There's a free one called can't remember which one we use at work. DB Browser, thanks Rob, which is totally free, does a job, also deals with SQL Cipher encrypted databases. You can put your password in there. So yeah, you can get access to the clear database and investigate what's going on there. Is everything loaded correctly? Run queries, run things through the query analyzer.
I had a quick question about the testability. So you talked about pushing complexity out of your app, which I could unit test, right?
Yeah.
And if I push that down into some complicated piece of SQL or whatever, like, how do you verify that? Like, what are your tools to verify?
Yeah, so it's a good question. So there is no unit testing at that level, right? So you've kind of got to do regression testing on your database schema and the data sets that you're dealing with, and be happy that the results are as expected. Yeah, I think the idea there is you're generally relying on the fact that your schema is going to be relatively stable and your kind of domain set is known. And then you can kind of do the regression test once and be happy that that's going to give you the good results, yeah.
You kind of just touched on it, but do you have any tips or thoughts on managing schema migrations for this sort of app?
Yeah, so GRDB does that really elegantly. So it has a whole a whole module that basically does that for you, right? So you can create a migration class that's unit tested, and on launch, new migrations will be executed once and once only, and the database will automatically keep track of which migration classes have ran. So yeah, it deals with that quite nicely, and you've got access in those classes to raw SQL as well, and you can do anything to alter tables or, update records, drop tables, add new tables.
Hey Steve, any tips for doing benchmarking outside of Query Planner?
Yeah, it's a funny area, Amy, because it's one of these areas I think where the answer is unfortunately always it depends. So you say, how fast is the query planner going to deal with this at this level of records in the database versus doing something in Swift. I personally have found that the database is always quicker. As a test, like we've got a test user at work with like 1 million transactions in it, and still find that it's very performant and able to spit things out. But unfortunately, it's trial and error. You've got to set up a testing scenario and just see how it goes.
Can you remember from the top of your head a good example of performance improvement that you got by pushing the complex to the lower levels?
I don't have any hard analytics, and again, going on from Amy's question, like it is a case where you would want to model that and just see how it goes. Model it on a real device, not the simulator, of course, and just see what kind of improvement you're getting. And we've obviously got to defend against premature optimization, right? Like you don't want to do a whole bunch of work that's going to result in a tiny change. But I think it can give you some notable improvements, particularly at scale. The way that you're able to return a set like a cursor, which means you've got the full results, but you're only putting in memory one record at a time, is really amazing compared to like asking for, perhaps 10,000 transactions in Swift that you're going to put in an array and try and filter. You're going to have some memory problems on some devices doing that.
Hey, Steve. So have you used it before with share app containers and just trying to open the DB using GRDB with app extensions and things like that?
You can do that, Pablo, particularly if you've got an open unencrypted database, so you're not dealing with credentials or secrets. That will work absolutely fine. Yeah.
Do you have any optimization tips and tricks for SQLite in general, like write-ahead logs and that?
Yeah. Again, it depends kind of situation. So do model it and do try it. GRDB themselves recommend that you use the database pool with wall enabled. It gives you the best performance. There are some trade-offs to that though. You're running at slightly larger risk of data corruption if things go really, really pear-shaped. But in terms of like modeling your schema, for example, these days sometimes you'll consider having a blob column that stores JSON, for example, if you just want to use that to present a screen and you're happy that you're never going to want to go deep into the JSON properties to search or filter. That might be viable compared to having like lots of individual columns. But in terms of like, well, how does that influence my, write speed when I ingest the records? Compared to all my, my indexing and things, if you really care, you've got to trial it out.
Hey, how would you compare GRDB with different persistence frameworks like Swift Data or, caught on a bit old example?
Yeah. For me, I'm happy to admit that I'm a bit of a control freak, so I like to be able to control everything. So as I said, like, when I use core data on applications, invariably things would go wrong at some stage, and I would feel kind of powerless that I wasn't able to go deeper to see what was going on and recover from that. I also prefer to work a little more closely with the raw SQL and do things like return cursors and return like joins that are not necessarily directly related to my models, if that helps me with what I'm doing. Swift Data is cool, but when I first looked at it when it was announced, it was like kind of, you got to use this on the view layer, not your view model layer, which I've still kind of not got my head. I know you can use it in the view model now, right? But I've not really revisited it or got my head around that yet.
So I'm assuming like being a banking app, accuracy is pretty important. How do you keep the local database in sync with, I'm assuming, like a cloud source of truth and like manage the life cycle of that data? Like what happens if the app doesn't log in for 25 days?
Yeah. Good question. So We have, as I said, we've got an open socket to the back end, and the only place we ever write we only ever write to the database from that socket. So the application never writes to the database itself. So we don't have synchronization issues, and we basically treat the local database as a cache, a copy of the cloud kind of storage. As a record comes in, we acknowledge using its ID back to the back end that we've safely ingested it. So we're quite happy then. The back end knows that it's written into the database, yeah.
Look what you've done with all your questions. Now we're at the back of the lunch queue. Hey, thank you so much. That was great.
No worries. Thank you very much. Thanks, guys.